Okay, let's see. Let's see, did I finish off the ionic and covalent bonding slides Monday, or is there still some slides left on that presentation, do you know? I'm gonna close some of these down. 'Cause these are not, these are biology presentations, so. My computer's been so slow today, and I'm impatient. I closed it down between my 10 and 11 o'clock class because it wasn't responding most of the time. In fact, I even got some not responding messages. And then when I did, it just took forever for it to open stuff and do things. But it seemed like the restart helped a little bit, but I think I'm just asking it to do too much. You know, run a camera, run a second screen, multiple things on my screen. I don't know. All right, people at home, can you see the slide for that?
Yes.
Okay, great, thanks. I'm gonna take a roll here. I think should have everybody in at this point. See people better. Okay, Lisa?
Here.
Okay. Taylor? Here. You are here in person. All right. Alyssa? Alyssa Cummings? Nigel?
Here.
Maddie Fleming? Brandon Faust? Aaron? Rebecca? Bronson?
Here.
Lindsay? Kale? Kale Hitchens?
Here.
Audrey?
Here.
McKenna Mooney?
Here. Here.
Okay. Cameron?
Here.
Maria?
Here.
Lazy? Lazy Schulte? Faith?
Here.
McKenna Wiggins?
Here.
Chloe? Janie? Okay, did I miss anybody? All right. Okay, so let's get over into the slide where I hadn't started this yet, had I? With you. I just finished off, what did we do Monday? Remind me. What's your last note from Monday?
The last note I have is about heat of formation.
About what?
Heat of formation.
Heat of formation. Okay. There we go. Okay. All right. So yeah, I was going to talk about ionic compounds. I think I did talk about that. I talked about how these page numbers don't match. And I talked about that because I was using the wrong presentation last week. I was using my biology class presentation. Had some of these same slides on there. Okay, but we got through that with the covalent bonds. And so I talked about electronegativity, actually. This is really, really faint, so I'm not really sure people at home can see it. If I hold it up in front of the camera, let me try. Bring it up there really close and try to straighten out a little bit. Okay, you see those numbers on that? That's like a periodic table, but it has the numbers written underneath it, underneath the symbols, okay? That's another version of the periodic table that's showing electronegativities. And I think you've got an example of that in your book. And then here's another one that is showing atomic radius. All right. And there's some trends of atomic radius and electronegativity as you go across the periodic table and as you go down the periodic table. And I have this packet that is not at all in digital format that I usually have students do every semester, and it's worth something. I got like in the past like 200 points for that one packet, I don't know if I'm gonna even mess with that this semester, trying to figure out a way to get you to do that. We kind of have it in some other parts, so I'll probably just stick with that. But I just want you to be aware that that's there. Okay, you can have access to that in chemistry. For finding out where these electronegativities, what they are, what the values are. okay? Because this talks about the value of, not all covalent, let me say this again. Not all covalently shared electrons are shared equally. That's the point these two slides are trying to make. If the difference between the two atoms is less than or equal to 0.5, then they have about the same ability to attract the electrons, and so they're going to be more equally shared between the two nuclei. But if you've got a difference of greater than that, up to 1.7, then one of those atoms has a greater attraction for those electrons than the other atom, and it's going to pull those electrons closer to its nucleus. And this happens and creates polarity. Okay, so your polar covalent bonds, things that are polarly made up of polar covalent bonds, are going to probably be polar compounds, so you exhibit this polarity. Above 1.7, if there's that much difference, then one electron or one atom is really attracting those electrons and going to hold it all the time, and that's your ionic bond. Okay, at that point, that's where we're talking about stripping electrons off of one and holding on to it completely. Okay, all right, one is just so much more magnetic, attractive than the other one in the group. All right. I've already talked about hydrogen bonding on the other presentation, so I'm not going to go back through that again. And here's where I think I kind of ended off, because I really felt like I needed a board and I needed some overheads, maybe to switch over to putting my Elmo up on the board to talk about this with you. So in the periodic table, okay, you need to do a periodic table with this as well. So let me see how this works here with my camera again. I think I was doing this a little bit last week. Whoops, okay. Okay. Okay, so I talked about cations, and your cations are over here on this part of your periodic table. These transition elements are almost always cations as well. You always have to put that almost always, because generally speaking, these act like cations. And then we get over here onto this side of the periodic table. Okay. This first column is going to be a cation. Okay, things in the first column 3, it should be A, so it'd be, this table is set up to be used for certain purposes of chemistry, in which case we refer to these as B's, but in your standard basic, they're A's. These are all B's, and these are A's. Okay. Yeah, it changes for purposes. All right, we'll get there. These are going to mostly be covalently bonded. They can vary, but mostly covalently bonded in here. But you get over to this, these last two columns before the noble gases, column 6 and 7, they're going to be your anions. Okay. And then you have the polyatomic ions that I directed you to in your book. On Monday, I gave you the page numbers for those. I don't remember it. It's not the one given in this presentation. So those are almost all of the ones in the chart, all of the ones in the table are polyatomic anions. They have a negative charge to them. If you flip back over to the page before that chart, and you look in the reading, there are 2 polyatomic cations that are given to you, the hydronium ion and the ammonium ion. And we don't use the hydronium in this class much at all, okay? So I want to talk to you then about how you name these. We'll come back to this iron 2, 3 thing like that. Okay, first of all though, Is that cutting off for you at home on the screen share, people? Are you able to see that full slide?
Oh,
It's
it's
cut.
cut.
It's cutting
No.
off. Okay. I don't know why it's doing that. That's new today. I mean, I've been having problems today, but that's a new one. I wonder if I'm like zoomed or something. Okay, let me close out of this. Hey, there we go. Maybe I'm not getting a split screen at all, right? Is that better?
I still can't see the full screen.
Okay, I don't know why, because that's all I'm seeing now. Usually I can see a split presentation screen. Okay, did that change things, people? What can you see now?
The full screen.
Got full screen? Okay, good.
Full screen.
Yay. Okay, so we'll come back to this iron 2 and 3 in a little bit. But right now, I want you to look at these rules for ionic compound names. And these are also in your book. And boy, my people in class here, they don't have the little window to see the top. So I'm gonna switch back and forth. That's probably gonna mess up my presentation slide too. Maybe not. Doesn't want to talk to it. There we go. Okay, now people at home, what are you seeing?
Black screen.
I didn't.
Wait, no, never mind.
Are you seeing the full slide still?
Yes.
Okay, great. Okay. Gotta get back to my page where I was. Okay. So rules for naming ionic compounds is the metal is named first. Well, the metal is again in those cation positions, those the 3A columns, 1A, 2A, and 3A, where you've got your cations. That's your metal. So you name it first, and then you go over to the non-metal, which is over on the other side. I'll put my periodic chart back up here in a little bit and talk about that again. And you're going to see that will be the second part of the name, but you're going to change the INE to IDE, okay? And that's when we write it. Okay, now here they're talking about also how to not just name it, but actually how to write the formula for it, okay? So I'm going to go through that a little bit too. Covalent names are different. They're composed of two nonmetals, and they can also have these double and triple bonds where we're sharing multiple pairs of electrons and stuff. So they have a slightly different approach to their naming, and that is that the first element is named with a prefix if you have more than one atom of that. Okay, so you use the second stem name, and then that's going to take an ending on it too. And there we put the "ide" as well in the naming, okay? And it may have a prefix if you've got two of those. So for example, carbon monoxide. We have one carbon. On the first one, we never put mono. Mono means one, di means two, tri means three, tetra means four, penta means five, hex is six, hept is seven, oct is 8, nona is 9, deca is 10. Those are all in your book. They're a table in chapter 3, I believe, okay? So they're in your book, and you do need to know those. Okay, so we've got one carbon, so we can say carbon. We've got one oxygen, so we're gonna say carbon monoxide to tell that we've only got one, all right? Here though, we now have one carbon with two oxygens. So we put the prefix di there. So we have carbon dioxide, okay? Now, above one, we're going to put a prefix in front of the first word two, in front of the middle, okay, or not middle, I'm sorry, but in front of the first element, if we've got more than one of those, okay? So this is going to be 2-di-nitrogen. We have an oxide again, but we've got 4 oxygens, so we're going to call it tetroxide. So dinitrogen tetroxide. And then, of course, we can get those polyatomic ions involved, which makes things even more difficult in figuring out what to call it, you know, but you just put that name on there. But that's why you get that little cheat sheet. You get a you know, smaller than calculator, smaller than phone size. It's a 3x5. No, it's not. Yeah, it is. I think so. 3x5 index card. You can use lined or not lined, but you can write your polyatomic ions on here. Right now, that's all that you can have on there. Okay, and I may add a few things as we go through the semester, but right now it's polyatomic ion. And when we take a test or quiz on Zoom, I'm going to want you to show me your card front and back before we start, so that I know that that's all you've got on there. Okay, and then when you use it, you probably need to hold it up so that you're not looking down. Because if I'm monitoring you through Zoom, okay, then and even Respondus with the web browser, they're going to need to hold it up so I can see that that's what you're using and you're not using something else, because web browser will, or the webcam on Respondus lockdown browser will tag you that your eyes have left the screen for too long if you're looking down at something. So you'll need to show me what you're looking at, okay, when you're referring to it. So I don't mind you referring to it. It's just that's, you know, something that will get tagged in as tests where I use the webcam. Okay. All right. So, but you are allowed that. In fact, don't come take a quiz or test from now on without it. You're just hurting yourself if you do, because you're going to want to refer to those polyatomic ions for things. Okay, more than just naming. Naming is just the beginning of all this. Okay.
Miss Rhoda,
Yes.
is it still on the same page in the book, the polyatomic ions?
Page. Hold on.
Page 11.
I stepped on my shoelace and untied my shoes. So let me get back over here where you can hear me better. The pages in this presentation are not right. Okay. The pages in the textbook from last semester are correct. I mean, we did not change textbooks over the semester. So if you're looking at an older textbook or textbook from last semester, those page numbers will be the same. But this presentation was made when we were using a different book. Okay, and I have not updated this presentation to reflect the page numbers. Mostly because this is a presentation that I have not used in years, because I typically don't do a PowerPoint with this presentation. But I felt like I needed to have something up there for the people at home to look at and refer to a little bit more. Generally speaking, I do this with like that packet handout, and it's all paper and pencil right here in class. So I went and found this, and I didn't think about the fact that this is old book in here, okay? So ionic arrangements of like salt, sodium chloride. This right here, these two little balls would be one salt molecule. The salt will form to itself many molecules to form a crystal. It looks like this. When it's large enough, you can see it. Enough molecules together does create a chemical we can see, but there's hundreds of, maybe thousands of those little molecules in a crystal that we can actually see. Yes, yeah, I don't want to talk about that. The electron dot diagrams, I'll show you what they are. That's what they are right there. Is we draw these little dots around the atoms. We put 2 on each side because that totals a maximum of 8. And with that, we can see that we're missing one here, you know, to be full, for that outer shell to be full. And that's all we're showing in the electron dot diagram, is we're just showing that valence electrons, those outermost electrons. I used the term valence on Monday. Use the curtains behind me to illustrate valence. Okay. I really don't want to get into spending time trying to draw those in this class because I don't think you need it necessarily. If you are having trouble visualizing electrons and how they're shared and stuff like that, that is something, it's a tool you can use for that. But I don't want to get bogged down in trying to have students learn that and figure it out, okay? Because it's really just a tool. And I don't know that we need it for things we're going to do in the future. So we have a structural formula that we can use, and we have a molecular formula that we can use. And here, those are illustrated. So this is showing the electron dot diagrams that you can use. We can use the structural formula, which is what I use mostly in this class. Is I draw bonds using these dashes. So every time you see a bond, that shows that there's an electron relationship going on between these two. It can be either ionic or covalent. If it's covalent, then there's equal, well, may not equal, but there's sharing going on of pairs. Otherwise, there's a give and take going on. This again, this is ammonia, okay? So this is the structural formula that showed it broken out. Over here, what I have is this is the molecular formula. This tells you the numbers of the atoms involved, but it doesn't show you how they are in bonding relationship to each other, like this does, okay, like that. So those are the differences, and these are the formulas we use in this class. We'll have molecular formulas, it's kind of like formula names, and then we have the structural formulas that are written out. Okay. So more commonly than anything else, we have methane. This is a gas, methane gas. It's 1 carbon and 4 hydrogens. Okay, and that's the beginning backbone molecule of all organic structures and molecules. Okay, all right. So from there, I want to have you practice with some time remaining. I may get into the next lecture too, but I want you to let's practice some naming. Let's go through some naming. Did I put up a sheet for that? I did. Okay. If you've noticed, I'm not showing my screen overhead. It's okay. If you go into the week 3 module, you'll see that I have put in some files for you. None of these are actually homework that you have to turn in for a grade, but they are all worksheets that I highly recommend you do, okay? There's a dose calculation rules. That's something that the nursing school wants you to start learning before you get there, okay? And I really want to share my screen to the people who are in class. And I may not be able to do that because my computer's moving so slow today, but I should be able to go into settings and do that. There we go. Okay. So you had measurements last week, and so this right here, this conversion key document, wait, it was duplicating. What did it do? Oh, so annoying. Okay. Yeah, I'm gonna pull this up, I think, this way. Ah, Peter's still going slow. And I think I'm getting frustrated giving it too many commands because it's not responding. It's making it worse. Okay. Go in here. Okay, I'm just gonna jump to this since I'm taking so much time here, and see if I can get my display to work again. So I'm gonna reset to show on only one. I don't know. Don't know why. Okay, so we're just gonna look at that conversion sheet, practice those conversions. It's just moving decimal points because I'm not having you change from English to metric. I'm just having you move within metrics, but you need to know, which is larger. Is a gram larger than a milligram, or is a milligram larger than a gram? Okay, kilogram, which is larger? Which is smaller? Liters, milliliters. Okay, just make sure you know those. That's what that little sheet's all about, is going over that and reviewing that. This one that I'm trying to pull up right here that is taking a while is a practice compound naming sheet. Okay. And like, wow, this has just been a day, I tell you what.
Can you hear me?
Okay, I don't know if that's going to open or not. So we'll just bypass it. Maybe. Okay, and we'll go back to the overhead. The Elmo. When all else fails, go to the Elmo, right? Let's see. People on Zoom, you can see the whiteboard again, right?
Yes.
Okay, great. I'm sorry, what? I'm not understanding you, what? Okay. So that one came up there. So anyway, this word, there it is. Oh, that's the solutions. Haha. I opened the wrong document apparently. Okay, you don't have the solution ones. So I'm just going to show you some examples of how to do this so that you can work your way through the sheet. I'll probably post those solutions a little later so you can check it out. But maybe not before the quiz, because I don't want you going and looking at the answers for the quiz if I have the same things on there. And I probably will.
This is measurement.
No, this will be next week's quiz. This is naming ionic compounds. Okay, so if you've got something like, well, we use sodium all the time. Let me pick something else off of here that's not so common. Let's look at like lithium, for example. Okay, lithium, we can have lithium and we can attach it to anything over here, actually in column 6 or 7. So if we want to have lithium fluoride, okay, we would write that as Li and F as its chemical formula. Okay, and then if I were to give you this on a test and say write out the name, you would just write it as lithium, that's the cation. And then you start writing fluorine, but you change the N to a D, which changes the pronunciation. So that you wind up with fluoride instead of fluorine. Okay? Sticking with lithium. We can have lithium oxide, oxygen, but it's our anion, so we put "ide" on the ending of it. So we keep the root of oxy. We take the "gen" suffix off of it and put "ide" suffix on it. So if we do that, though, we've got to look at something. Okay? Our lithium is in column 1, which tells us that we have a +1 potential there. We've got 1 electron we could get rid of, leaving us with a positive, extra positive in their nucleus, okay? And oxygen wants to gain 2 more electrons, so it has a -2 potential. All right, so in order, though, to make this happen, lithium can't give oxygen 2 electrons. It's only got 1 to give. But if we're going to have a bonding relationship between these 2 elements and only these 2 elements, then we're going to have 2 of these, right? And 1 oxygen. Does that make sense? Because if we were to write it like this, when we form the compound, we have to have a neutrally charged compound. If we were to just put Li and O together, lithium and oxygen together, we would have 1 more negative than we have positive. So we would have a negatively charged compound, not a positively charged compound. And we don't want that. But if we put 2 down here, now we have 2 positives. So that gives us a +2 total overall up here to balance our -2. Okay. And in your little worksheet there that it gives you, I think it tells you about the crisscross method. When you're dealing with something like this, you can actually, to write the subscript by writing the superscript of the other partner. So this 2 would come down here and this 1 would come down there, except you don't write 1s. 1s are assumed. You just leave the 1s off, okay? So let's look at something a little more difficult then. Let's come over here to column 3 and look at aluminum. Everything in column 3 has a +3 potential, okay? So if we were to write aluminum, there's our symbol for aluminum, and let's go ahead and put it with, well, let's do the easier one first. Let's put it with fluorine. So this is a +3, and we put it with fluorine, which has a -1. Well, how do we make that balanced? A neutral charge. How do we give that a neutral charge? Okay, right. So if we have 3 fluoride atoms to 1 aluminum, then we can have a neutrally charged compound. Because aluminum's got 3 it wants to get rid of. Fluorine only needs 1. But if you've got 3 fluorines, that aluminum can give 1 to each fluorine. Okay, so yeah, we would just write 3 here. Now see how the crisscross method works? The 3 from here comes down here, the 1 from here goes there, but you don't write the 1, you just leave it. So your formula in the end would look like this. You don't write all those positives and negatives on your final formula either. You can do that on scrap paper while you're trying to figure out, you know, how many to put there. But in your final answer, you would always have it cleaned up.
And then
Okay.
if you're naming it, just be aluminum and then fluoride.
Right.
Is that how you would name it?
Yeah. So the naming on this is aluminum fluoride. Okay.
And you don't put the 3.
You don't. Yeah. No numbers in the name.
Okay.
Just in the formula, okay? So yeah, and this up here, I didn't write it out. I'm off my screen, okay. This is lithium. It's not a cube. Made my X too soon, okay. Oxide, oh, and that's usually not capitalized. Second name is usually not capitalized, okay.
So we don't have to put the 1. We just gotta assume that it's 1.
Right, that's correct. You don't write the 1s, you just, but you do everything above that, 2s and 3s. Okay, so another aluminum example here that's a little bit problematic is let's do aluminum, and let's do aluminum and oxygen.
So it'd be -2, 3.
Okay, yeah, so aluminum is still +3, nothing has changed there.
So you do 3 oxygen, 2 aluminum.
Yeah. Okay, let's look at that though. Let's see what. Okay, so a crisscross method, if you use crisscross method, which is it's not really a cheat, but I usually don't teach it to you this early. I usually make you go do the worksheet and then come back to class, and then I'll teach it to you. I make you do it the hard way first, because I want you to understand why the crisscross method works and what it really means, and not just, oh, I could put this number here and that number there. Okay, so yeah, if you put the 3 down here and the 2 there, it's a neutral charge. Why is that? Because aluminum has 3 to give away and oxygen will take 2. So if I were to have an aluminum and an oxygen here, well, aluminum can give 2 of its electrons to oxygen, and then it's got its -2 full. But aluminum has still got 1 more it wants to get rid of. So, well, here comes another oxygen in, right? It'll take it, but it still has, that's only -1. See, it's got a -2. It wants to take 1 more electron. It's got potential to take 1 more electron. So that means we've got to get another aluminum involved, so it can share 1 with it. So now we're up to -2, but now it's got 2 it wants to get rid of. Well, okay, let's bring another oxygen in. See? 2 aluminums, 3 oxygens, balances it out. If we represent that here with our 2 aluminums, 3 oxygens, then also we can look at our charges here. 2 positive 3s gives us a +6 total on this side. And 3 -2s gives us a -6 on that side. So we have a nice neutral compound. Okay. Visual on that good for people? Kind of, okay. All right. So yeah, you can put the 2 here, you can put the 3 there, do the crisscross method, but like I said, I really want you to understand what's going on and why that works. It's not just magic, okay? All right, and yes, we would call this aluminum oxide. Okay, what's my time look like here? Okay, got just enough time, I think, to talk about ions. Okay, so as I was mentioning earlier, that most all of these transition elements here can be cations. So they can work in the ionic compound arrangement as a cation. Everything, also, when you look at this periodic table, and it's in color in your book, so it's a little easier to see some of this. On the periodic table, everything that's on the left side of this stair-step pattern, this bold-faced stair-step pattern, everything on the left side of that is considered a metal, except for things that are like here, which are also highlighted on the periodic table in your book. So go check those out and look at those. If they're touching the line, except aluminum, if they're touching the line, then they're called metalloids, okay? But the big divider here is everything this side is metals and everything this side is non-metals, except for some of these things that touch the stair step. Metalloids can have properties of both metals and non-metals. So there's the transitions there, okay? So metals can act as cations. And so let's look at like iron, for example. Now, why these things here are called transition elements is because it's not a hard and fast rule how many electrons they want to get rid of. They all have 2 valence electrons in their outer shell. So most of the time, these things are going to have 2 electrons available for ionic bonding. But for some strange reason, these things here can and do, okay? And I don't know if people can actually, yeah, you can see the screen there, okay. So I don't know if I need to stand it up or not. Okay. These things, some of the electrons that are further down in the next shell can get involved in reactions too, okay? So therefore, they can transition from how many they have available. And these itty bitty little numbers right here, okay, I think in your book you've got something similar, I think similar location on the chart. Those tell you the possibilities. So you probably can't see it here, but iron has 2 and 3. So iron can either give up 2 electrons or it can give up 3 electrons. If it is giving up 2 electrons in a situation, it's called iron 2. If it's giving up 3, it's called iron 3. So an example of that would be if you've got iron oxide, which iron oxide is that?
2.
It's either 2 or 3. There's no iron 1 because we just talked about how many electrons. Okay, yeah, it's the first possibility, but we don't, and that confused me as a student too when I first learned this, okay? So because we know this is a -2, then this has to be the +2 potential one on that, okay? So yeah, this is, and it's written as iron. We use Roman numerals, iron 2 oxide. Okay, how about this one? It's iron chloride. Okay, so if this is a -1, then that means we've got a -3 charge on this side. So this has to be the +3 version of iron. So this would be written as iron 3 chloride, okay? And we can have an iron 2 chloride as well. That's just this, okay? So you have to look at your anion to tell what the charge on it is to determine what your charge on your iron is. And then when you write out the name, you name it appropriately. And the Roman numerals always go in parentheses. Okay? All right, so that should get you started on your naming compound sheets. I'm over time, so I'm gonna quit. Do those, bring those questions to class Friday. All right, we'll go over it. Let me clarify that. We'll go over your questions. If you don't have any questions, I'm moving on to covalence. Okay. I'm going to assume that you did it and you understand every bit of it. Does anybody have questions?
I might come up with questions Friday.
Okay, and I'll be in office hours today from 2 to 4, and of course I'll be in office hours for lab tomorrow from 1 to 3. So if you have anything, you can come in there. Doesn't have to be lab related to come into there if you have questions or problems. Okay. And Nigel, what was your question?
What worksheet?
They're in module 3.
Okay.
Okay, just go in there and look at those. You know, print them off if you can. If not, you can just scrap paper from the screen type of thing. Yeah, I think you will want to write them out.
Yeah.
Yeah. Do I have more online questions?
It's not a question, but I emailed you about not being able to make it to lab in class Friday.
Okay, yes. All right, so we'll just, we'll get with, next week, get with me and we'll see a schedule of when you can make that stuff up. Okay? I'll
Okay.
look it back up for you. If that works for you, that'll be
Yeah.
great.
And I can send you my LOI if you need it to, just like for proof that I'll be at drill.
Right. Yeah, if you can send me a digital copy of that email, that would not be bad for me keeping a file.
Okay.
In case somebody asks, that rarely happens, but okay. All right, other questions?
What about my attendance? How does that affect with me being sick?
Let's see, if you have a doctor's note, just email me a copy of that.
Okay, I can do that.
Yeah.
I'll have her give me one.
Yeah, email a copy or you take a picture on the phone of if you've got a paper. If she didn't give you paper,
She
it's like school nurse didn't give you paper, you can go ask for one and I'll give you one after the fact.
Okay.
But just email me a copy, a picture, phone picture,
Okay.
copy of it would be great.
Okay.
Okay.
Yes, ma'am.